Yes, that is correct. I am a business guy in an uber geeky kind of a world with this world of supercomputers and HPC. So what I share with you today is my perspective from the lenses of business. And that sometimes is helpful and at other times scares people. So anyway, we will want to describe what that just might be like. So from a perspective of large scale and small scale, I want to share a perspective and will here about the macroeconomic impact of supercomputing, and not to be forgotten really is the microeconomic impact. The two being very different. The macro tends to be where we have national policy and where we fund computers on a national scale, large dollars. But at the micro level, supercomputers actually help companies do what they do better, and I'll describe some of that. And in that micro space, universities can help, but industry and companies also invest in supercomputers in some very unique ways. It includes some of the R&D, but supercomputing now is well out of the R&D departments in companies and fully integrated into operations and design, and therefore more involved with deployment and demonstration, deployment of product. So intimately involved in product design if we're a manufacturing company, and ultimately integrated with decision making inside companies. So let me start with the macro, high-level, national perspective. Just recently, as in 2 weeks ago, the United States White House made an announcement to launch a strategic computing initiative. This initiative looks at HPC and supercomputing as a strategic investment as a nation. No real surprise there. This is a little bit like 1982, where supercomputing for open science was considered a new thing to do at that time. Historically, supercomputers around the globe have been funded for purposes of defense. So in the 1940s and 50s, we all were trying to defend ourselves better, and wartime drove investment in computing. And in fact, the early digital was fully in order to support wartime. That has changed a bit, and now others are involved in the supercomputing investment. But this new initiative here in the U.S., I just wanted to share with you because it has several important points that you can see on that slide, but I'd like to share here 5 specific objectives that came out of the White House this week. And this is fairly important for us to remember. We today are at the petascale level for computing. Petascale is 1,000 times bigger than terascale, and that's 1,000 times bigger than the gigascale that we had before that. So exascale is now officially on the radar for an American strategy. But interestingly, there is a desire to be a bit tighter in the coherence between the classical modeling simulation that takes place in computing and data analytics. They're suggesting that these two need to come closer together. At the same time, they wish to establish a path that will get us beyond what are the perceived barriers today from Moore's law. So if we cannot continue semiconductor development like we are today, we need to get a step change. We need to get a different path for developing that technology. Interestingly, bullet number 4 that addresses workflow has not been a conversation in the supercomputing lexicon here recently in these years. So workflow and networking algorithms, software, these are all needed, and we know that. But historically, the primary emphasis in supercomputing has been the processor itself, the speed of the processor, the floating point operations, and the power of the processor. We are now finding barriers in supercomputing that are other than the processor. So this number 4 is very interesting. But number 5 is where I will speak mostly to today. And that is the public-private collaboration is now understood as important, if not necessary, to actually achieve economic impact. So let me move forward. Blue Waters is a very large supercomputer here at NCSA, and it was built to run at a sustained petascale level. Here's the machine itself in a slide. There are nearly 300 racks, 24 nodes in every rack, nearly 25,000 computers in this system. With that, these 4 rows that you see here have about 30 petabytes of disk storage in these 4 rows. Everything we do with the supercomputer is really around speed. We try and, in fact, desperately need to have great speed in order to accomplish things rather quickly. Now, we need some scale with that at times, but speed matters. So literally 300 racks away, physically, latency can be a problem in a supercomputer. So if you can imagine, you get 2 computers side by side to talk to each other, that's far easier than to get a computer to talk from the other side of the room. So that latency, all of that distance actually matters. So the speed at which we move data between this disk storage system and the supercomputer itself is the fastest in the world today at 1.5 terabytes per second. Terabytes per second. So lightning fast. We can load up a petabyte in short order. So these speeds trickle down into other things. So the reason I mention this is the trickle down effect becomes real. The speed can then manifest in other ways. It can come about in more commodity supercomputing after we do these things and actually make them happen at the supercomputing level. So the speed at which this occurred here in Champaign has never been achieved before. The vendors had never done this before. Cray itself had never built a computer this big before. So in the very special world of high tech, supercomputing is a special place because no one tends to build the things at this scale without the investment that comes in national investments at this sort of scale. Let me move on to a manufacturing example. Most of supercomputing investment from nations and governments is focused on scientific discovery. In fact, the leading nations around the world actually want scientific discovery. We all know that science matters when it comes to pushing forward in very complex ideas. However, in manufacturing, this discovery is not enough. The fidelity that comes with this and the time that it takes is exceedingly important in a manufacturing environment because it must happen within the design time that they are given for a product. That design time at one major manufacturing company that we have here in Illinois, the designers are given 2 weeks. Possibly the entire time to market for a product could be 6 months, might be 9 months. Maybe from the initial time, I believe the large companies want to have this cycle in months and not in years because it is just too costly. So if in that entire launch time, the designers are given 2 weeks, This particular manufacturer in R&D was trying to do modeling and simulation of the oil in the differential of a large tractor. 2 or 3 iterations of that model with the complexity of the physics, that computer run was taking 2 months, a single run. But if the designers are only given 2 weeks, that means all of the supercomputing is going to remain in the R&D basement forever and never see the light of day into the production cycle. So the challenge in manufacturing is to get the speed and the scale to the point where it can be done within the regular productization workflow. So that's one of our challenges as we work with industry, is to always be paying attention to the workflow, and this is a good graph, good example. Let me also suggest that the research that takes place on supercomputers and at universities would be at the left side of this chart. Theoretical, basic research, all at the left end. And if the full product rolling out the door, heading off the dock, is on the far right side of this, the path to get from research to product has to go through the prototyping and development, and we want to demonstrate something, we want to deploy it, we want to optimize, we want to make sure we have the right kind of product. So we live in the middle. We at NCSA, particularly in the private sector program, live in the middle. So I would suggest, by living in the middle, that we actually help bridge this gap. In fact, that's one of our missions, really, is to help companies do what they do better, faster, and get it to fit inside the workflow that they have. Companies need to de-risk, and they need to run through the uncertainty. They need to lower risk and lower the uncertainty when they try to bring a product to market. Classical supercomputing does not address that. Classical supercomputing is science-oriented discovery. So we try to take what is best out of that classical market and deploy in a different way in how we engage with industry. And that touch with industry actually becomes the economic impact. Now, there's not a lot of funding that occurs there in the middle. This picture comes from our US government and shows that most of the funding in theoretical research comes from government and universities. Most of the funding on the product side comes from the private sector. If we look at Silicon Valley, we look at other technical industries, lots of that funding comes from venture capital, startups, entrepreneurial activities. There are not many funding streams that address the middle, and that becomes a gap. Specifically, some of the reasons that, or the ways in which our private sector program engages is with pure HPC. We also work with software, we work with data, and we try to map applications to particular hardware to be able to marry this up and actually improve the productivity of the use of computers with industry. We have worked with 40% of the US Fortune 50 companies, about 60% of those manufacturers. In fact, of the Fortune 100, 18 companies are manufacturers. Manufacturing is a sector that had adopted supercomputing early on, mostly because of the code base and the engineering codes that had used 3D design in the early days, driven by defense. And then early adopters included aerospace, and those codes, specifically the solids and fluids, those kinds of designs have made manufacturing one of the longest running sectors to use supercomputers. Today, we also have biotechnology, oil and gas has used it for quite a while. But anyway, manufacturing has been a long-running sector, and we have expertise at NCSA to help address that. So this valley of death that is in the middle where there is very little funding is to be bridged in both a macro and a micro sense. So inside companies, I have GE tell me that the GE Global Research Center, their R&D center, has to sell what they do in the research side to the business units. That bridge they have is their own valley of death, because some decision maker, they will sit around the room and say, okay, I want this and this, and these other things we cannot afford. No funding, this won't move on. At the macro level, we have the same thing. In the marketplace, we also have the valley of death. We could get something researched, an entrepreneur tries to bring it to the marketplace, maybe it fails. That valley is something to be bridged, and computing can actually help lower the risk and the uncertainty that occurs in that valley of death. I want to state here that certainly volume drives down costs, but it's the business drivers that we want to pay attention to in looking at economic impact. Not just the capability of doing something because it is digital, but we want to be able to address the business drivers. If we do that, the impact becomes very real. We change behavior. Actually, breakthrough science can change behavior. One of the things that we've done recently here in our private sector program is begin paying attention to commercial software vendors. The commercial software codes, particularly in the manufacturing space, have been unable to scale and have been regarded by many as poor examples of what supercomputers can actually do. So lots and lots of doubt that these commercial vendors could scale to the levels at which we were building supercomputers today. I'm happy to suggest here, and I've got some slides a little bit later that will share this. We have made breakthroughs in this space by treating the ISVs with a lot of care and a lot of love and saying, hey, we'll love you more, come on in, let's try a few things, and we've been successful. Our people skills matter. My team down here in the far bottom right corner really matter. And we need the domain expertise, we need computer scientists, we need the understanding of HPC, and we need government in the room. We need to be able to affect policies and a lot of things. Most of the barriers to reaching economic impact with supercomputing today are cultural and behavioral. We invest in a lot of computers, but the way in which we use those, the organizational structure around access models, and the way in which we work the software, those barriers are very much driven by cultural and behavioral attitudes. The drivers for industry, I mentioned the decision-making capability. These drivers really are around product. In order to understand how a business operates, one must know how that decision process comes about. All decisions in a large business come around a product line. OEMs, original equipment manufacturers, large companies that assemble things like planes, tractors, cars, those kinds of things, they have a supply chain. They also sell to very distinct groups of customers. Those customers matter, they buy the product, so if we cannot tie that modeling and simulation to a specific product, then it only will be in the R&D department, and R&D does not have enough budgets to move the dial very far on changing behavior. A significant driver in industry is reduced cost and reduced time to market. A classical business case about 15 years ago came from Goodyear Tire Company. Goodyear was not doing so well. Took a lot of time to come out with a new product. It very well may be that other companies in the tire business were the same way. It take well more than a year to get a new tire design to market. And Goodyear decided that it was just killing them because it was taking way too much time, way too much cost. So they put pressure on their head of R&D, pretty significant pressure, and said, we must get this design time down to months, not years. The head of R&D basically says, well, my goodness, if we do all our prototypes, it takes longer to cure rubber than that. We can't get this down. That process is just simply too long as we prototype these things in a physical way. So they very intentionally adopted digital techniques, 3D design, trying to lower the uncertainty and lower the time. They were successful in doing that with a particular tire design that was launched, and they got the design time down to less than 6 months. They got in the process, physical prototyping was reduced from 40% of R&D to 15%. And they saved $100 million in the process. Some would argue it may have saved the company. So they put a big bet on going digital. It's a classical case study on how the reduced cost affects the health of a company. This slide depicts the companies that I have that partner with us at NCSA today. In the top left are the manufacturers: Caterpillar, Deere, Dow, GE, Rolls-Royce, Procter & Gamble. I am rather amazed at how much digital technology goes into Procter & Gamble's products. Who knew how much digital technology goes into making diapers? Who knew that the nozzle on a bottle was high engineering? I didn't know until I learned from these folks. So I can imagine and understand better how Dow, when they make bulk liquid products, and how P&G, when they make bulk liquid products. There's a lot of chemistry going on, a lot of things there could be digitized and so forth, but also really extreme importance is how effective the bottle line actually moves when bottles are being filled. So lots and lots of modeling goes on in places that are not in making the product, but also in or not making the ingredients for the product, but in making the product in a final packaging sense. We also partner with the oil and gas industry. You see there ExxonMobil and BP and BHP Billiton. These folks in oil and gas use seismic echo sort of techniques to be able to determine underground whether they're seeing dirt or water or oil or salt, so that they can understand where to drill for oil. Huge billion-dollar bets on where to place drill for oil. Lots of use of supercomputing. In the bottom left, we have some companies in the ag and life sciences space. Syngenta has some remarkably similar challenges in plant genomics to Mayo Clinic's human genomics. But those two companies wouldn't necessarily be going to the same conventions together or even see each other on a normal basis. So we in computing have a chance to be able to cross that divide, learn from each, and actually bring innovations to the other if we see things that make sense. We're also working now with AbbVie. I don't have that logo on the page, but AbbVie is a pharmaceutical spin-out from Abbott Labs. And in the pharmaceutical business, lots and lots of computing is needed to be able to reduce all of the compound designs that will not work and try to get to the point where they understand the compound designs that do work. Very interesting, just in the last year, I believe one company by the name of Cycle Computing had helped Novartis use Amazon Web Services, tens of thousands of cores, I believe is what it was, a relatively modest amount of money, and they were able to do some things on the Amazon Web Service with high-performance computing that they had never been able to do before, and achieve some real significant results. So all sorts of places are benefiting from that these days. Looks to me like that I have a picture here, it's not totally showing up, but IFORGE is the name of our computer that is not government funded. We have Blue Waters. Blue Waters was a $200 million supercomputer. Takes about $35 million a year to keep it running and keep it fed and watered and maintained. IFORGE is a machine that we have put on the floor to serve industry directly. No government funding, no government rules. I sort of like that. It is a supercomputer for industry. It allows us to do these advanced 3D designs, particularly in the engineering space. We also have on the same computer the ability to run data analytics. We're running R. If any of you, that is a statistical and analytical software application. We're running that on a supercomputer. That has not been easy. The data analytics has tended to have a different architecture to be able to run well. Google invented Hadoop to be able to do some data analytics very well. Hadoop has not been able to be installed on classical supercomputers easily. We have attempted to do that with Blue Waters, but these communities of data analytics and classical design computing have not, up to now, lived well on the same kind of platforms. But we're doing some of that now. This iForge really is designed to be workflow friendly, and we run it at high uptimes, and have even done a live upgrade, taken a chassis, depowering a chassis one at a time, and upgraded the entire system node by node without ever powering down the entire machine. That is not typically something that we would see in a very large supercomputer. About 4 weeks ago, we made an announcement together with Caterpillar where we are hosting some of Caterpillar's services. So again, the classical uses of supercomputing by manufacturers include finite element analysis, which is structural analysis, and CFD, computational fluid dynamics. We need to know the airflow almost everywhere in a machine. We need to know the structures when we build machines. Those classical engineering codes run very well on iForge. So we spent a year and a half with Caterpillar to help them understand how far we could push the codes that they were using. And we were able to help them understand that our business is HPC. So we were able to improve the productivity of those codes, improve how quickly they ran, improve the behaviors and the practices of their personnel. And by the time we were done with that 18 months, they basically said and began to wonder themselves whether they should be hosting HPC in all cases, and said, why don't you do some of this for us? And we did. So that's a new thing for us. The classical example in the world today has been HLRS in Stuttgart, Germany. They host services and do a lot of dedicated work for Mercedes-Benz and Porsche. Now those companies are in their backyard and in the same county or state, if we call it that, over there in Germany. They do some very, very impressive work with those companies. So we're proud to say that we're beginning the same path here with Caterpillar. We also do lots of work on our systems with Rolls-Royce Corporation out of Indianapolis. That group in Indianapolis makes jet engines for Rolls-Royce. Some of the ways in which we need to engage include partnerships. We had a pilot here just a while back in the Midwest that worked with 4 large companies, John Deere, GE, Procter & Gamble, and Lockheed Martin. And an interesting thing happened. We were hoping to help their suppliers. Handpicked were 2 suppliers of each of these companies. We then helped with trying to improve their modeling and simulation. If they were doing that, we also had one company that was a supplier to John Deere that had not done any 3D modeling and simulation on a computer. All physical prototyping. They built very large hydraulic tubes for things like the boom on the front of a tractor or the boom on a fire truck, so forth. All physical testing. We expected to be able to make changes in their modeling and simulation capability. We expected dramatic changes. What we didn't expect were some of the changes in behavior. So John Deere, by trying to find a couple of their suppliers for this pilot, they went to their procurement department, which typically says, let's go look for people who can build to specs that we provide and build to those specifications. We want the lower cost. We want the classical business things. What we learned is, what John Deere learned was they had never asked their supply chain who was doing modeling and simulation and who was not. Never occurred to them. Never asked. They do it at the high level. They did not know how that was happening at the low level in their supply chain. So that's a behavioral change that we found by working the business side of this with some companies. That was not a digital breakthrough by any means, but it certainly was a behavioral breakthrough. We also were instrumental in pulling together groups of companies to form a new institute. Several years ago, the White House organization decided to put together a network of innovation institutes, public-private co-investment, and one of those institutes is in digital manufacturing and design innovation. Classical use of supercomputers to do the design side, but on the manufacturing floor, not much of high-end computing had been used. And as you can imagine, lots and lots of data is driven from a manufacturing floor. So what this institute is attempting to do is to bridge those areas in manufacturing with data with the design data. And once you go to manufacture a specific product after it's been designed, classically that as manufactured product has never been able to be compared back to the as designed products. There is a gap. If that gap was narrowed or closed, we might begin to improve the manufacturing process with the final objective of 0 defects. It's never happened before. It is one way to use big supercomputing because of the data equation and the design equation. This use of supercomputers would be very, very different than the way we have done this with national investment in almost every country in the world. I have begun to work with countries and supercomputing centers that work with industry. Most of these have pretty much self-identified. You see the cities here that have centers that we've begun to work with. So we're trying to get a dialogue going about with the communities that serve industry, because the way in which we serve industry differs greatly from the way in which we serve academic and governmental science. So wide variety of industry sectors, wide variety of countries, wide variety of software, and lots of fun in doing so. This community came together and helped contribute to a book that just came out in this year that I co-edited with a colleague from Amsterdam. And that book has examples of industrial use of HPC in it as well. It's one of the first times we've been able to share real case studies. Europe has a number of engagements in helping small companies, the SME communities, the supply chain, so to speak. This target to help the suppliers do more work with supercomputers is an admirable one. The funding is up to 250,000 euro for a lot of these collaborations. And what we know is that lots of suppliers have no access to advanced computing, and therefore they do not use advanced computing processes in their design. So this is a very good example in Europe as to how that is making a difference. South Korea has something similar, working with SMEs, the small communities. They've worked with more than 300 here in just the past few years with clear reductions in cost and their development time. Now the key here, however, is will these small companies that get help from these programs ever change their behavior? Will they, in fact, move on and invest in the computing tools that they were taught how to use and do that on their own? What is the analog for a small company to do what Goodyear did and reduce the cost of physical prototyping and invest more in digital? We don't know. We don't know the answers to that yet, but that in fact is the objective. How can we change the behavior? Lots of ideas on this slide. I just reduced it to one, but this is a software working group with our U.S. Council on Competitiveness. One of the biggest barriers to the use of supercomputing is indeed the software itself. Not many places have been investing in software. Not many nations invest in software. Certainly the United States of America does not do this in a broad sense. National investments are rare in software. Our country's attitude is the market should take care of that. But in supercomputing, the advancements in architecture and the hardware have advanced so far, they have outstripped the capability of the software to run on that hardware. As we approach and address exascale computing, as the processors themselves changed, we have placed a huge burden on the software folks to be able to keep up and actually write the software that addresses these fast-changing technologies. So gaps in funding, gaps in capability, and these are some examples on this slide of comments from our software working group saying that greater access would actually accelerate innovation, but by the way, I can't hire a computer scientist from a university that even knows what's in a supercomputer. We're rather proud of what we do with computer science here at the University of Illinois, but even we take on criticism as not graduating people who are computationally aware. Not just to understand the computer science side, but to understand how these supercomputers actually work and how the applications would be in chemistry, in physics, in a number of other things, in biology. Cultural issues have this bias, so a number of things in here. At the very end, I want you to just remember that the business drivers will indeed pull technology, and they don't really do that well enough yet today. So there are shared problems at the macro level. In software, the academic communities have trouble with software. Industry has difficulties trying to write software. Government itself has difficulties writing software that's going to work. Just count the number of times that our various agencies and others have been hacked. Cybersecurity is a huge problem. Shared problems. There ought to be a way that we can come together to get some fixes by sharing in the solutions. We know that no single company, no single federal agency, and I don't believe any single government can fund everything. So when I was in Melbourne and Canberra earlier, it might have been last fall that we were there, learned a lot, all sorts of opportunities. You folks do a lot of things in the applied sense that we don't do here in America. I've got a code in Japan that does multiphysics very well. Got a code in Barcelona that does multiphysics very well. And that's a huge opportunity, but we don't do much sharing between countries, and I think there is an opportunity there. And I just say at the bottom bullet here that if speed wins, then more collaborations are necessary. This is the book that came out. Just want to let you know 11 countries had contributed, 40 different contributors actually helped write case studies, and it really is a global overview of high-performance computing and high-performance data analytics. We're rather proud of it. I learned a lot of things. I wrote this in mind, like the introduction and history, for a non-technical reader. I want my wife to be able to read this book. I want government people to be able to read this book. I want decision makers at the C-level inside corporations to be able to read this book. None of those are computer geeky enough to be able to read a computer book. Most of the HPC books that are out there are on the technical side. So this is very different and actually shares some of the synergies and the opportunities in addressing the business side of this. So let me just share a few breakthroughs here. And the last 2 years, we worked with Blue Waters and our team in the private sector program. LS Dyna had run to about 500 cores, wouldn't even run very well to 1,000. By collaborating together, we got it to 15,000 cores. Fluent, we got to about 15,000 cores, which was a match of what they had done before. Eventually got it to 36,000 last year. Just last week, we doubled that to 67,000 cores, and just yesterday got it to 102,000 cores. What's magic about 102,000 cores? Well, nothing, except that their competition was at 102,000 cores last year. CD DAPCO, that star CCM plus code, we got that to 102,000 cores last year. So lots of collaboration is making some headway into bridging the gaps with software. So lots of fun, totally unfunded. Nobody's paying me for this, but we're doing it because it matters. Because manufacturing as a community uses commercial codes. Much of the design, much of the discovery community that does science on supercomputers writes their own codes. A lot of academics write their own codes. Very few of those codes ever see their way into business, and is particularly into manufacturing. So these commercial codes really, really matter when it comes to performance and productivity. So we're paying attention to it and seeing some breakthroughs. The way in which multiphysics matters, there are 3 good examples here. A human respiratory system, a kiln furnace, even a beating human heart. The physics is similar in each of these cases. So if we can help a commercial code perform better, we can address some manufacturing, we can address some human health issues with similar kinds of physics and similar capabilities in the code. One other very, very good example has been a biomedical discovery by Klaus Schulten here, who is a power user on every supercomputer he can get his hands on. His code has been funded over 20 years by our National Institutes of Health. And what he has done is looked at the atom level of a virus. What this picture is on this slide is an HIV virus. The shell to this virus was not well known. The reason the shell is important is because if the shell could be understood, perhaps there's ways to put glue in all the gaps in that shell and keep all the bad stuff inside. What they learned in the shell is that it actually has functions that they could not have known otherwise. And their models that they were able to run on a supercomputer were 1 billion atoms. 1 billion atoms. The reason that's important is because at the atom level, at the atomic level, this cannot be done in a wet lab. This cannot be done with a microscope. You might get to a molecular level. So supercomputers will make a difference when the application has issues that are very small, too small to see otherwise, or such large scale that it wouldn't be able to be done in a physical lab. However, that was a static cell, non-moving. The objective for human cell analysis means that they need to understand how 1 trillion atoms work together, not just 1 billion. That's 1,000 times more. That would be exascale computing. Now we have a use, other than some of the obvious ones, for pursuing exascale computing. Let me suggest that the business side of this needs several things. We need really good domain expertise, whether it be atoms in a biology setting, the atomic level of fibers in a manufacturing setting, whatever that may be, we need the domain expertise. Now at my university, you folks may be the exception, we don't teach the domain folks much about computing. And likewise, we don't teach the computer scientists much about a domain. So we need those two talents in the room together. The domain folks and the computer scientists and the mathematicians, those who can program. We need to get them in the same room. But those two folks have also never been taught HPC. They've not been taught supercomputing. They have not been made computationally aware, even at many of the best universities. So now we need all three people in the room to be able to get something done and to be able to get some impact on this innovation. But the three of those are not yet good enough. We need a fourth person in the room to be able to translate the business drivers, the consultants being able to assess and look at the strategy as to why we need to invest in this or that. So my suggestion here is we have 4 legs to the stool, 4 pillars that are absolutely required, and supercomputing centers, HPC centers, are wonderful places to bring all 4 of those under one roof. And I say that because our observation is that innovation is what's required to convert inventions into engineered products and services. Ask around the universities, if we look at the academy, if we look at the things that are invented in a lot of offices on campuses, many of those things remain on the cutting room floor in those offices and do not see the light of day. We need some folks who can bring those to bear and be very innovative. And I say that because, and this is just about my last slide here, is because I believe in this. I went out to actually look at some of the tenets that were in the original book of The Wealth of Nations. Productivity determines standards of living. Productivity of workers is enhanced by, and look at that, specialization. That would include supercomputers, the high performance computing work that we do, the very advanced 3D modeling and simulation. That specialization improves productivity. And that can be specialized, or that specialization can be made possible with more scale. So it's my opinion and observation that the national wealth, that the wealth of nations can only be enhanced if we increase the wealth of the industry in those countries. So if we only invest in the long discovery, science, and do not bring that more forward into industry, we will miss that accelerator in the economic impact. I'll leave you with that. That's my story, and I'm sticking to it.